Welcome. On this video, we will talk about the convergence and divergence of a sequence. So let's start by discussing this small introduction question, which states, here we have an explicit formula. We don't know if this sequence is geometric or arithmetic, we just know that it's a sequence. And what we want to do is first find the first six terms. So let's find those terms. So the first term, the second, the third, the fourth, fifth, and 6. So again, in order to, since we do have an explicit formula, all we gotta do is just plug in n equals to 1 to get the first term. So we're gonna get 1 plus 1 over 1 squared, which is 2 over 1, which is exactly 2. To get the second term, all we gotta do is plug in n equals to 2. So we're gonna have 2 plus 1 over 2 squared. So that's 3 over 4, which is approximately 75. And if we continue doing this, you will see that the value for the third term, this is going to be 0.44. For the fourth term, that's 0.31. For the fifth term, that's 0.24. And for the sixth term, that's 0.194. So, okay, we got the first six terms. And now let's plot the values and the terms in the sequence. So for that, we're going to use a small Desmos activity. So for this activity, notice that at least for the introduction question, this is the equation that we do have here. So let me plug this in 0. Okay, so this is the equation. This is the explicit formula that we had initially. Notice that that's n plus 1 over n squared, but at least in Desmos, I have to represent it as x. And here we got our first term, which is 1 comma 2, which is exactly what I got here. Because from here, I would have got a coordinate point at 1 comma 2. From here, I would have got a coordinate point at 2 comma 0.75. From here, I would have got a coordinate point at 3.44. From here, I would have got a coordinate point at 4.31, 5.24, and 6.194. So these are going to be the coordinate points that I'll be reflecting on my Desmos activity. So that's exactly the first point. So this is when n equals to 1. So now let's see, for the second term, we're going to get 2 comma 0.175. So if I'm just going to extend this to n equals to 2, so notice that this is when n is equals to 2, which is exactly 2.75. That's exactly there. So now if we continue doing this, notice that this is where we would have got our third term, n equals to 3. And if I continue moving this, let's see where my fourth term would have been. This is when n equals to 4. N equals to 5. And lastly, n equals to 6. Okay, so this is exactly the coordinate points that we gotten from our calculations here. I'm just prefer to do it under Desmos than to actually plot them here. Okay, so now that we have properly plot the values and the terms in the sequence, let's use the limit notation and try to identify what is the limit of the sequence as the n is getting larger and larger. So now the objective now is to see, is it possible for me to identify the value that this sequence is going to approach as I keep getting farther and farther on the sequence? Well, let's see. We can do this by observation. So my first term, it's right here. My second, my third, my fourth, my fifth, my sixth. Let's see. Let's find the seventh term. So here we got the location of the seventh term. Now let's find the eighth. And let's find the 9. And let's find the 10. And let me zoom out a little bit here. Oh, I guess. Okay, so I guess I'm going to keep going. I was like, now, one thing that we should notice here. Okay, so let me just erase all this. One thing that we can notice here is the following. Notice that we seem to be approaching a certain value as I getting farther and farther on the sequence. Because notice that this is my 4, the 17. Notice that as I keep getting larger and larger on my sequences, I seem to be approaching a value. I seem to be approaching a value. Notice that if I were to keep, let me keep increasing the value of my sequence here. Um, Let me find it up to 30. What would happen if I keep finding more sequences, more terms in the sequence? Notice that if I keep increasing my terms, I seem to be approaching the value of 0. And I don't seem to be going any farther to the negative, so I don't seem to be going upwards at all. It seems like as I keep getting farther and farther on my sequences, I seem to be getting closer and closer to the value of 0. And perhaps this is the limit. So if I keep getting farther and farther, so as n gets larger and larger, I seem to be approaching 0. So the limit of the sequence, it's of a value, and this value, it's 0. So using the limit notation, the way that we can define it is that I seem to be approaching the value of 0. And this is an example of what we call a convergent sequence. And we're going to define that in a second. But at least keep in mind that this is one example of a convergent sequence, because notice that the limit of the sequence, it seems to be approaching a value. And again, it doesn't always have to be 0, but at least the idea of a convergent sequence is if I keep getting farther and farther and farther on my sequence, if I keep taking a look at the value of the terms in my sequence, if I seem to be approaching a certain value, then we call the sequence a convergent sequence. Now, let's take a look at the other example here, which notice that it is essentially the same expression. It's just flip. It is the same explicit equation. It's just flip. But now, let's try to do the same analysis here. Let's start by finding the first 6 terms in the sequence. So again, let's try to find them. My third, my fourth, my fifth, and my sixth. Let's try to find the value of those terms. And again, to find the first term, all we got to do is plug in n equals to 1. So we're going to get 1 squared over 1 plus 1, which is 1 over 2, which is exactly 0.5. Now for the second term, let's plug in 2. So we're going to get 2 to the second over 2 plus 1. So that is 4 over 3, which is approximately 133, 1.33. And if I continue doing this, the value for the third term is going to be 2.25. The value of the fourth term is 3.2. The value of the fifth term is 4.1. And the value of the sixth term is 5.14. And now that we have those 6 terms, let's plot the value of those terms in our graph. And again, for that, I'm going to use this decimal activity. So let's go to our decimals. Let me clear this out. So let's close the introduction question since we're not talking about that anymore. Now notice that we're going to be discussing this new sequence, which is exactly the sequence from the first example. So x squared over n plus 1. That's what we do have here. So now let's activate the actual terms in the sequence. Oops, because I already gave it away. So here we have our 0 term. So notice that the value of this term, so this will be the value of my first term, which it seems to be true. So we should have got a point of 1 comma 0.5, which that seems to be here. Now let's plot the second term. Seems to be true. 2 comma 1.33 seems to be about there. So now let's keep plugging more terms in the sequence. So let's plot the third term. We got it there, which should have been 3 comma 2.25 seems about there. So 1, 2, 3, 225. That's fine. Now let's get the fourth, the fifth, and the sixth. So we would have plot those values. This is what we would have gotten. Okay, so the pen's not working. That's cool. So this is what we would have gotten here. So this is my first, my second, my third, my fourth, my fifth, and my sixth term. Now, though there seems to be a pattern here. Well, not notice that at least on the other one, it seems like it was approaching zero. But at least for my second sequence here, if I keep plugging more values on my sequence, so that's my seventh term, 8, 9, 10, 11, 12, notice that it doesn't seem like we're approaching a very specific value, because if I keep plugging more terms of my sequence, I seem to be just increasing without a bound. So I don't seem to be approaching a certain value. So if I keep getting farther and farther away from my sequence, if I keep, well, here, I'm going to say that we already plot them here. So if I keep getting farther and farther from my sequence, or if I keep getting, or if I keep plugging higher and higher terms in my sequence, I don't seem to be approaching a certain value. I seem to be just increasing without a bound. So therefore, the limit of this sequence, we can say that is positive infinity, because notice, let's plot more points. So instead of 30, let's go to 40. Let's plot more values here. So that's my 30th, 31st, 32nd, 3rd, 4th, 5. So if we keep plugging more values in my sequence, I'm just going to keep increasing without a bound. Like I'm just going to have some kind of a line that is going straight forward, going up. So therefore, the limit of the sequence is positive infinity, since I keep getting closer and closer to higher values of y. And this is an example of what we're going to be referring to as a divergence of a sequence, or divergent, or a divergent sequence, where a convergent sequence, let's close this, a convergent sequence was a sequence that seemed to be approaching a certain value, which in this case, in the introduction question, we seem to be getting closer and closer to zero. So we're going to say that the sequence converges to zero. Now for our second example, let's close this. For our second example here, we are quite the opposite, because I was getting farther and farther from my sequence. So if I keep getting larger and larger terms in my sequence, I don't seem to be approaching a certain value. I seem to be just increased without a bound. So therefore, we call that a divergent sequence. So this is a small example of what a convergent sequence and a divergent sequence is. So let's just define very loosely. Let's define what a convergent and a divergent sequence. So a convergent sequence is an example, just like the introduction question, where one way to think about convergent sequence, it's a sequence that approaches a value. Which in this case, we were approaching the value of 0. And a divergent sequence is a sequence that does not approach a value. And we can either have three types of divergent sequence. The first one is that it increases without a bound. Which is exactly what we had on the first example. And we could also say that, well, it could decrease without a bound. Or the last scenario that we could encounter is that if it keeps jumping from value to value, so if it keeps switching, from one value to another in a cycle. So this was just a small lesson where I wanted to introduce to you the idea of what a convergence and divergent sequence, but it pretty much a convergent sequence is a sequence that just approaches a value if we keep getting farther and farther on the sequence. And a divergent sequence is a sequence that does not approach a value, and it does not approach a value because it either increases without bound, decreases without a bound, or if it keeps switching from one value to another in a cycle. And again, it's very important for us to represent those conclusions using the limit notation. We have to use the limit notation to properly indicate if it's a convergent sequence. So if the limit of the sequence as n gets larger, it's equal to that value. So this is the value that it converges to. And if the limit was infinity, then therefore it is divergence. We could also have negative infinity, or we could say that it does not exist.